as I gave you a teaser last time, today we're basically gonna focus on how we can compute things like every time we go to Olympiads, we have like these questions that ask us to compute the last digit or like the second last digit or something like that. We're going to focus on a very easy way on how to do this, but today's session is going to be mainly revolving around proofs. It's going to be a very proof-heavy session, but because if we're only proving things, that's boring. So we are going to do a little competition. Since we have two groups, I'll give you some hints on proving a very important theorem in number theory, which is called the Euler-Phi function. So the group that can come up with a proof faster, I will buy you some things at the Smiley Cafe. Is that a good stimulus? Okay. So basically, but before that, let's recap. So last time I was basically focusing on notations and like a really classical technique in number theory. It was mostly, I think, of the greatest two takeaways. The first one is modulus, where if P is congruent to Q at mod M, this means that these two have the same remainder when divided by M. So modulus is basically denoting it is just basically denoting the remainder of an integer divided by an integer. And then the second thing I think is quite significant, and it's going to be very much used in today's proof, is factorization. And factorization is really important because in number theory, when we deal with numbers, when last time we had the proof where we had to do prove that something is, I think it was this, whatever, it was this kind of problem. And then the technique that we used was to basically break this number down into smaller numbers, and then take that approach where we consider each of the factors of this number, whether the factors can divide this one, and then dividing the proof into three different sections where we consider 2, 3, 5, we were able to get the proof. So I think factorization is also one of the biggest takeaways from last session. So a very classic way in number theory or how we would write factorizing a number is, let's say we have an integer n. And when I use this notation of z with two lines, it just basically means integers, okay? So let's say that I have an integer n. Then, usually when we factorize something, we write it the general form as like this. So basically all numbers are going to follow this format, where they can be broken down into the multiples of these really small factors and then some power of these. And then this detail here is important because this is basically saying that each one of these are positive integers, 2 to the power of 4, 3 to the power of 2, and 5 to the power of 1. So you can see how this number can also be expressed in this form. So basically this is like the most generalized version that we can write integers in. So that's that. I'll leave this part here because this is going to be important. And then what we want to get today is something called the Euler-Phi function, which is denoted as, this is the small phi. This is probably the big phi, or you can also write the Euler-Phi function as this is the Greek small phi, but I prefer writing it as this. So the Euler-Phi function, what it basically does is that it calculates the number of coprimes to n that are smaller than n. And you might be thinking, what the hell is this? So I'll give you an example. Let's think about phi 10. Let's write all the numbers from 1, all the integers from 1 to 10, okay? So we have 10 numbers. Then this one is basically calculating the number of co-primes to n. So the co-primes to n, if we get rid of the ones that are not co-primes, 2 is not a co-prime, 4 is not a co-prime, because 4 has a common divisor of 2, 5 is also not a co-prime, 6 also isn't, 8 isn't, and 10 obviously isn't. So you have 4 left. So the Euler phi function value of 10 is going to be 4. And then, if you think about prime numbers, if we think about phi 7, this one is the only number that's not co-prime. So phi 7 is going to be 6. And this is going to be a hint for the proof that we are going to be doing today. So that's basically what the Euler phi function is. The reason why this is significant is going to come out soon, but basically the task that we are going to focus on is to find how this form can be expressed into. So a generalized form for the Euler phi function. The first hint is this. The second hint is this about how this phi function computes when you have primes. And the final hint is that if m and n are co-prime, pi m times n is phi m times phi n. You don't have to prove this theorem. We're going to prove this lemma soon. You can just take this one for granted. So the first task is to come up with an expression for pi n. So like, is it a polynomial? Is it like n to the power of 4 minus something n to the power of 3 or something? Or does it involve like cosines, or does it not? Like, yeah. So the coming up with the basic form, that's the first thing to do. So this is our lemma, and then let's talk about what the Euler phi function is going to be. So the first bit of hint was factorization. The second bit of hint being about phi prime numbers, and the final bit about this property, and this property in general is called a multiplicative function. If a function can be expressed in this form, where the thing inside the function equals its factors multiplying, then we call that a multiplicative function in that case. So the Euler phi function is like a basic example of that. So getting these three hints together, the first thing that we want to do is to express this n in this factorized form. Because looking at this, I don't know what phi 10 is going to be before I actually compute it. But computing these prime numbers, we know that the only divisor of a prime number is 1 and itself. So logically speaking, a prime number inside the phi function would always be the prime number minus 1, because you only take out the prime number itself. So this means that it's relatively easy to compute when the number has only one factor, when the number has only one prime factor. So we'll factorize the number into different bits. So we can firstly express pi n as phi all of these, but then we know that each of these p1, p2, and pk are prime numbers, so they're co-prime to each other. They do not have any common divisor, which means that we can apply this property here. We said that if m and n do not have any common divisors, then pi mn would equal pi m times pi n. So we can apply that thing to here. This one, this one, and this one, all the way up to this one, have no common divisors, which means that we can express that as the product of each of these. But then here we tried 7, which means that if we have a prime number P1, pi P1 would equal P1 minus 1. But then consider that, well, now consider P1 to the power of Q1. Because when we had P1, we write the numbers all the way up to P1. And the only one to remove was this. But now we have more than that. We have P1 plus 1 all the way up to P1 to the P1 times 2 minus 1, P1 times 2. So this is the numbers that we now have to consider. In the case of P1, it was only this row, but now we have P1 to the power of Q1 minus 1 number of each of these rows. So we have to take all of these out, and then this block here, excluding this column, would be the number of prime factors that are smaller than this number. Does everyone understand this part? So if we think about actual numbers, if you're thinking about Euler phi function of 3 to the power of 5, if you're only considering phi 3, we only have to get rid of 3. But now we have this all the way up to 3 to the power of 5. So we have to get rid of this entire column. So basically, this entire column, we have 3 columns because the prime number here, the only prime factor is 3. And we got rid of 1 column, which means that if we generalize this back, before we generalize it, which means that the number of prime factors smaller than 3 to the power of 5 is 3 to the power of 5 times the number of columns on the denominator, which is 1, 2, 3, and then 2 on the numerator, because we have 2 columns that are surviving after we get rid of this entire column. So you see here, you can see the pattern here. Pi P1 to the power of Q1 would equal P1 to the power of Q1 times P1 minus 1 over P1. If you look here, P1 minus 1 is the number of columns that remain. And then P1 is the number of total columns. Because if we have P1 columns and if we make only P1 minus 1 columns remain, then we should multiply this to the entire number of integers that we have here. So this is the first step to gain the general form. But then now we can just apply this to each one of these. Because just as P1 to the power of Q1 can be expressed in this form, P to the power of Q2 would be also expressed in the same way. So this becomes P1 to the power of Q1 and just for clarification, can everyone see this? Is this visible to everyone? Okay, so P1 to the power of Q1 times 1 minus P1 over 1. Because this just basically equals this, and then this would just be 1 minus 1 over P1. So we can express this into this, which is probably the simpler version. So we can apply this to each of the 5 functions that have only 1 prime factor inside it. And then it's going to be this form, But note here that if we take each of these out, if we reorder this, so that now we have these numbers at the beginning. So these ones have got to here, and these ones have got to here. This thing here just equals n, because that was how I defined it. So it's just basically n times this, and that will be general formula for any integer of n. Is everything clear? Okay. So this is basically the first part of the proof. And then we did get the answer. We can actually try this for really large numbers. And then I have a graph here, which is kind of interesting. Before we go into proving this thing that we took for granted, this program here is called Wolfram Mathematica. If you guys have used Wolfram Alpha to do your math homework, this is like the advanced, that stronger version of that. And it's super expensive. So here, this is the code that basically makes the coordinates of each of the numbers as the x. So it's basically like x comma pi x. This is the coordinates of each of the numbers. So 1 comma pi 1, 2 comma pi 1, 3 comma pi 3. So, and then this is a graph of that when you do it until 10,000. And here you see like these really small, is this visible to everyone? Okay, I'll just enlarge it. So here you have these, it isn't that visible, but there still are little gaps in the middle. But then if I change this to 100,000 instead of 10,000, then the lines become much thicker. And then there still are these small gaps in between, but there are even more lines that kind of separate the gaps. So the gaps are even smaller and narrower. And I honestly have no idea why this is happening. So if you guys are really interested in number theory, you might actually write an EA on this in the future, or maybe this could even be like university stuff, like undergraduate stuff. I don't know why this is happening, but this is just an interesting property of Euler phi functions that I just found. So this is the first part of the proof, but we've just taken this one for granted. We don't know why this is true. So let's try to prove this. And then, because we're kind of running out of time, I'll give you 8 minutes to discuss this with your table people. And then when you guys are proving this, the thing is, when you are proving this, you should not use this, because this result came from assuming this. So if you use this result to prove the assumption, that will just be like, the logic will just go round and round. So it doesn't make sense. So you cannot use this property to prove that that thing is true. You have to prove that in a different way. And there are 2 hints. The first one is to write numbers in this kind of way that we did for proving the Euler phi function. The second hint is let's say that I have m and n that are coprime, and I have numbers 1 to n minus 1. Then if I multiply m to each one of them, so if I have m, 2m, 3m, all the way up to and if you guys do not want the hints, you guys can just not listen to this. And the final one, we have n minus 1 times n. Then, if you take this one is congruent to this one at modulus n. So the order is obviously going to differ. This one might be 1, this one might be like 4, this one might be 7, but still only the order is different. If you have this set and this set, each of the elements of this set under modulus n is going to be exactly the same as this set that you have here. So that's the second hint. Okay, so let's do the proof for this final hint. I personally think that the proof for this one is kind of cool. So let's first prove that pi to the power of pi mn equals phi n phi n. And then the first thing that I gave you was this one about writing the numbers in m times n squared. So that's what we're going to do. Firstly, we start with 1, 2, 3, all the way up to, should we do n rows or m rows? Just m? N, okay. Let's do n rows. Which means that we should have m columns. And also just an additional reminder that mn is coprime. So it will probably look like this, I assume. Yeah, if I haven't made any stupid mistakes. The shape of mn numbers will probably look like this. But then, you see the previous hint where I told you that if we multiply m to each one of these numbers from 1 to n minus, 1 to actually n, 1 to n, then that equals, that is congruent to this. We will apply that back to here. Here we have m numbers, so this under modulus m, each of these are different, right? So the number of coprimes in this row is pi n, pi m, because you have m numbers, and if you want to know the number of coprimes to m, that is just basically pi n. So this is the number of coprimes to m in this row here. And then for this row, for this row as well, we have phi m co-primes to m inside here, because this is basically n times this, and we already proved that, not proved, but we also took this kind of for granted, but the other bit of hint tells us that each of these are going to be different under modulus m. So under modulus m, this is also going to be pi m, the number of co-primes to m in this row. But then for this one, things become a little bit different as this number in front of n starts to change. Because the number in front of n, let's say that this number here, let's say that m is a factor of 2. But then if m is an even number, half of these are not going to be co-prime to m. And then in that case, the number of co-primes to m isn't pi m. So you have to think about the number of rows that have co-primes to m in the very first place. Because some of the rows might not have co-primes to m in the first place. Because if we have a row where we have Rn plus m, and then R is a factor of m, then this entire row would just basically not have any co-primes. So we think about the number of rows, and that is basically pi n. Because when we're thinking about the number of co-primes to, because we now have to think about the number in front of n that becomes a co-prime with n. So that number is phi n. So we have phi n rows that have phi m co-primes. Which basically means that if we multiplying these two, we eventually get phi m times phi n co-primes. And then this is how we prove that phi mn, which is the number of co-primes inside this entire thing, equals phi m, which is the number of co-primes in each row, and times phi n, which is the number of rows that have phi n co-primes. But then then another way of proving this would be, this is an algebraic proof, and some of you might think this one to be an easier proof. I also do. So using the principle of inclusion exclusion, we have in total mn numbers subtracted by the number of integers that are divisible by m, and that is going to be mn over n. Because if we have 1 to 6 and we want to know the number of integers that are divisible by 3, we just divide 6 by 3, and then we get 2, which means that we have 2 divisors of 3 inside 1 to 6. So mn minus mn over m minus mn over n. But here we have to be careful, because inside these mn numbers, we have divisors of m, divisors of n, but then if we subtract each of these from mn, this part is the intersection that we subtracted twice. So we have to add the number of elements in here again, which is basically this, right? Because this part here is the number of integers that are divisible by m times n, by both m and n. So calculating this, we get mn minus m minus n plus 1, which is m minus 1 times n minus 1. And then we knew for a fact before proving this that the phi function of a prime is just basically the prime minus 1. So this equals to pi m, this equals to phi n. So phi mn is the product of phi m and phi n. This is another alternative way of proving this theorem. So the two kind of like go hand in hand. The first part was actually this part needs to come before what we did. So because phi is a multiplicative function, we can apply it to this generalized form for every single number of n, and then we get this generalized formula. So that would be the complete proof for why the phi function looks like that.